In your entire life, you have never seen an object. Not your phone, not the moon, not your own face. You have only ever seen light. And here is the uncomfortable part. Nobody knows what light is. Einstein spent 50 years on the question and admitted he failed. Then, in July of 2025, a Nobel laureate's lab at MIT finished the cleanest experiment ever aimed at it, and the answer they confirmed is stranger than anything Einstein feared. Tonight we follow that story all the way down, through collapsing theories, backward-seeming time, and heretics who doubt the speed of light itself. So dim the lights, get comfortable, and stay with me, because what they found in that basement changes what you saw today. Part 1. The experiment that should have settled it. In July of 2025, in a laboratory at the Massachusetts Institute of Technology, a team of physicists finished an experiment that was 100 years overdue. The lab belonged to Wolfgang Ketteler, a man who already owned a Nobel Prize for chilling atoms down to the coldest temperatures ever achieved in the universe. His team had spent months building what they called the most stripped-down, most idealized version ever attempted of the most notorious experiment in all of physics. And when the results came in, they confirmed something genuinely unsettling. The picture of light you carry in your head, the one you have trusted every waking moment of your life, is wrong. Not slightly wrong. Not wrong in some technical detail that only matters to specialists. Wrong at the root. Let me describe the picture I mean, because you almost certainly have it. Light, in the everyday imagination, is a kind of bright something that travels. It leaves the bulb above your head, crosses the room in a straight line, bounces off the page or the wall or the face of someone you love, and arrives at your eye. It is a thing, out there, moving through space, existing whether or not anyone happens to be watching. A ray, a stream, a messenger with a definite route and a definite nature. That picture feels so obviously true that questioning it sounds like philosophy rather than physics. The MIT experiment was designed to question exactly that picture, and it was designed as the final round of an argument between the two most famous physicists who ever lived. In the 1920s, Albert Einstein and Niels Bohr began a debate about whether light has a definite nature of its own. Einstein insisted that it must. Whatever the strange new quantum mathematics seemed to say, he believed that a particle of light is a real thing with real properties, and that any fuzziness in our description reflects our ignorance, not reality itself. Bohr held the opposite position, and it is a position that still sounds outrageous a century later. He argued that light has no fixed character at all. It shows you a wave when you ask a wave question, a particle when you ask a particle question, and there is no fact of the matter about what it was before you asked. For 100 years, that argument could not be fully settled, because every real experiment came with clutter. Real slits cut into real barriers, real detectors with real imperfections, 1,000 places for a skeptic to say the apparatus itself was muddying the answer. So the MIT team removed the apparatus almost entirely. They cooled more than 10,000 individual atoms to a few billionths of a degree above absolute zero and held them in place with crossed beams of laser light, spaced out like an impossibly tiny crystal. Each single atom became a slit. Then they turned the lighting down until it barely existed at all, so faint that each atom would scatter, at most, one single photon, one atom, one particle of light, and nothing else in the way. No barrier, no machinery, no excuses. The smallest possible question put directly to light itself. And here is what the light answered. When the atoms were prepared so that they kept no record of which atom a photon had bounced from, the scattered light overlapped into an interference pattern, the unmistakable signature of a wave. When the atoms were prepared so that they did keep a record, even a faint one, the wave behavior faded, and it faded in exact, smooth proportion. The more information the universe held about the photon's path, the less wave there was to see. Not a switch flipping between two modes. An exchange rate, precise and continuous, between identity and information, landing exactly where quantum theory said it would land. The team published the result in Physical Review Letters on July 22, 2025, and the conclusion was difficult to soften. Bohr was right. Einstein, on this question, was wrong. Light does not have a nature that exists on its own, waiting to be discovered. What light is depends on what can be known about it. Sit with that for a moment, gently, because this is not a fringe claim from the edge of science. This is the confirmed result of the cleanest version of the experiment ever performed, run by one of the most respected laboratories in the world, agreeing with a theory that has never once failed a test. The everyday picture, the bright something travelling along its definite path, has now been ruled out about as thoroughly as anything in physics can be. It is remarkable how quietly this news landed. There were headlines for a few days, mostly framed as a sporting result. Einstein loses again, and then the world went back to its scrolling. But think about what was actually confirmed. The substance that delivers every sunrise, every photograph, every star, every glance between two people was shown to have no definite character of its own, only the character that circumstances draw out of it. If a chemist announced that water had no fixed nature until someone tested it, civilization would pause to take a breath. Light received the same verdict, and barely anyone looked up from their phones, which were, of course, busy beaming light into their eyes at that very moment. Part of the reason is that physicists themselves were not surprised. Quantum mechanics had been predicting this outcome for a century, and the theory has a habit of being right. The MIT result did not overturn the science. It removed the last sliver of room for doubting it. There is a difference between suspecting something uncomfortable and having it measured, though, and 2025 is the year the measurement arrived. Here is what I want to do with you tonight. I want to walk through how we got here, slowly, because the road is the point. Every single model of light that human beings have ever constructed has collapsed under close inspection. The ray collapsed. The wave collapsed. The particle collapsed. The polite compromise of a little of both collapsed one photon at a time. And in 2025, the last comfortable idea that light at least has some definite character independent of observation collapsed in a basement in Cambridge, Massachusetts. Along the way, we will meet a wave that arrives as a single dot, a traveller that crosses 10 billion light-years without experiencing a single second, an experiment that appears, at first glance, to reach backward in time, and a small society of heretics who suspect that even the speed of light is not what we have been told. None of this needs to be solved tonight, least of all by you. The universe has been running on these strange rules for nearly 14 billion years without our permission or our understanding, and it will keep running while you sleep. So let the strangeness arrive at its own pace. Before we visit any laboratory, though, I want to start somewhere more personal. I want to start with the light entering your eyes at this very moment. Because there is a fact about your own everyday experience that you may never have noticed, and once you notice it, it changes the stakes of everything that follows. The fact is this: in your entire life, you have never seen an object. Not one is less than break time equals 1s is greater than number. Part 2. You have never seen an object. You have never seen this video. You have never seen your phone, your bedroom wall, the moon, or your own face. That sounds like a riddle, but it is a plain description of how vision works. Every visual experience you have ever had was built from light, and only from light. Photons leave a source, strike a surface, and some of them ricochet into the small, dark openings of your pupils. Your retina absorbs them, converts them into electrical signals, and your brain weaves those signals into a picture. The picture is all you ever get. The objects themselves stay forever on the far side of the messenger. You have spent your whole life reading letters and have never once met the person writing them. On a bright afternoon, the scale of this correspondence is hard to hold in your head. Something on the order of 100 million billion photons pour into your eyes every second, a number so large that counting them at 1 per second would take longer than the age of the universe. Your visual system samples that flood, throws most of it away, and sculpts the remainder into the seamless world you walk around in. And the system is sensitive to an almost absurd degree at the other end of the scale. The rod cells lining your retina, the ones that handle dim light, can respond to a single photon, 1, the smallest possible unit of light that the universe permits to exist. That last claim is worth slowing down for, because it was actually tested. In 2016, a research team led by Ali Pasha Vaziri built an apparatus that could fire 1 photon at a time toward a human volunteer sitting in total darkness, and then asked the volunteer to report whether they saw anything. The volunteers did better than chance. A human being, made of roughly 7 billion atoms, can consciously register the arrival of 1 single quantum of light. Think about what that means for everything we are going to discuss tonight. The double-slit experiment, the quantum strangeness, the wave that is also a particle, none of it is confined to laboratories. Your own retina is a quantum detector. The arena where light performs its strangest behavior includes the inside of your eyes. Your sensitivity to light has a famous real-world benchmark. On a clear, dark night, away from city glow, a standard candle flame is visible from roughly 1.6 miles away. At that distance, only a small handful of photons from the flame enter your pupil each second, and your brain still says, "There, a light." You are, among other things, a photon-counting instrument of remarkable quality, and you were issued this equipment at birth without a manual. The instrument even tunes itself slowly while you wait. If you have ever stepped from a lit house into a dark yard, you know the first minute is nearly blind, and that the stars seem to multiply the longer you stand there. What is happening is chemistry. Your rod cells rely on a light-sensitive molecule called rhodopsin, which bright indoor light bleaches away, and rebuilding the supply takes time. After 10 minutes in darkness, your sensitivity has climbed enormously, and the process keeps going for half an hour or more, until your eyes are operating near the physical limit that the universe allows any photon detector to reach. Astronomers guard this dark adaptation jealously, using dim red lights at their telescopes, because red light spares the rhodopsin. There is something pleasing in the thought that the oldest stargazing advice, "give your eyes time," is really an instruction to let a quantum sensor finish calibrating. And the picture your calibrated eyes assemble is never a picture of now. Light takes time to arrive, so every act of seeing is an act of looking into the past. Across a room, the delay is a few billionths of a second, meaningless to you. But look up on a clear night, and the delays sprawl. The moon is a second ago, the sun is 8 minutes ago, the star Sirius is 8.5 years ago, and the faint smudge of the Andromeda Galaxy, the most distant thing visible to the unaided eye, is 2.5 million years ago, light that left before our species existed. The night sky is not a scene, it is a collage of different pasts, pasted onto a single black ceiling, and your brain flattens it into a moment without telling you. But here is where the everyday picture begins to wobble. The light arriving in your eyes does not carry colour. Colour is not a property that exists out there in the world. What exists out there is wavelength, the physical spacing between the crests of an electromagnetic wave. Red light has a wavelength of about 700 billionths of a meter, violet about 400 billionths. Your brain takes those measurements and manufactures an experience, the redness of red, the blueness of blue, entirely in-house. Some colors do not correspond to any wavelength at all. Magenta has no place in the rainbow. There is no magenta photon anywhere in the universe. Your brain invents it on the spot whenever red-sensitive and blue-sensitive cells fire together, papering over a gap in the spectrum with a color it made up. And the spectrum you can see at all is a sliver of what is actually there. Visible light spans wavelengths from about 380 to about 700 billionths of a meter, roughly 1 octave, in musical terms, of an electromagnetic keyboard that runs for dozens of octaves in both directions. The room you are lying in right now is crisscrossed with radio waves carrying conversations and songs, microwave light, infrared, glowing off your own warm body, all of it the same physical phenomenon as the lamplight you can see, and all of it invisible to you. A creature with different eyes would describe your bedroom as a completely different place, and that creature would be no more wrong than you are. Even the sources you trust are stranger than they look. An ordinary bulb, putting out the visible light of an old 60-watt incandescent, releases on the order of 10 million trillion visible photons every single second. Each one of those photons carries a tiny, definite parcel of energy, about 410 billion billionths of a joule for green light. Brightness, it turns out, is just counting. A dim room and a bright room differ in how many photons are in flight, the way a drizzle and a downpour differ in drops. Now, let the real point of this part settle in. Light is not just one source of information about reality. For your senses, at the scale of the universe, it is essentially the only one. Every star you have ever seen, every photograph, every telescope image, every measurement of the cosmos, arrived as light or was read out by light. Our entire picture of reality is hostage to the character of this one messenger. If the messenger turns out to be strange, the strangeness leaks into everything it ever told us. And the messenger is strange. That is the thread we are going to follow all night. Every era of science produced its confident answer to the question of what light actually is, and every single answer fell apart under close inspection, one collapse after another, right up to July of 2025. I will admit that telling you that you have never seen your own face is an odd way to help you fall asleep, and I promise the strangeness from here on arrives gently, but it does arrive. The first collapse came more than 2 centuries ago, and it was delivered by a quiet physician with sunlight, a sliver of card, and a result so simple a child could repeat it, aimed squarely at the most untouchable scientist who ever lived. Is less than break time equals 1s, is greater than number, part 3, the ray and the wave. Isaac Newton believed light was made of particles, and for about a century that settled the matter for nearly everyone. He called them corpuscles, tiny bullets of brightness streaming from luminous bodies in straight lines. It was a sensible picture, and it explained a great deal. Shadows have sharp edges because bullets travel straight. Mirrors work because bullets bounce. The corpuscle theory had problems, especially with the way light bends as it enters water, but Newton was the man who had explained the motion of the planets and the falling of the apple with the same law. Disagreeing with him in public was, for a long while, simply not a career-enhancing move. There was a rival picture, even then. The Dutch physicist Christiaan Huygens proposed in the 1670s that light was a wave, spreading outward the way ripples spread on a pond. The wave picture handled bending and spreading more naturally than bullets did, but it carried an awkward question on its back. A wave is a disturbance in something. Ocean waves disturb water, sound waves disturb air. What does a light wave disturb? Empty space appeared to be empty. Wave theorists eventually conjured an invisible medium to carry their waves, a substance they called the luminiferous ether, said to fill the entire universe while remaining undetectable. Keep that ether in mind. It is going to die later in this story, and its death will matter. The man who toppled Newton's bullets was Thomas Young, an English physician born in 1773, and possibly the most relentlessly capable person of his era. He could read at age 1. By his teens, he had worked through more than half a dozen languages, and as an adult, he made serious contributions to medicine, to the physics of elasticity, and to the decipherment of Egyptian hieroglyphics. In 1801, he turned his attention to light, and he performed what may be the most consequential, simple experiment in the history of science. Here is the whole apparatus. Let sunlight pass through a narrow opening, then let it fall on 2 slits sitting close together, side by side, and place a screen beyond them. If light is made of Newton's bullets, the prediction is easy. Bullets fly straight, so you should see 2 bright stripes on the screen, one behind each slit, like spray paint through 2 gaps in a stencil. That is not what appears. What appears is a whole series of stripes, bright, dark, rippling outward from the center, including bright regions in places no straight-flying bullet could possibly reach, and dark gaps in places bullets should have peppered freely. Young understood immediately what the stripes meant, because he had seen them before in water. When 2 sets of ripples cross on a pond, there are places where crest meets crest and the water leaps higher, and places where crest meets trough and the surface goes still. Overlapping waves add and cancel. The stripes on the screen were the same arithmetic written in light, where the wave from one slit arrived in step with the wave from the other, brightness. Where they arrived out of step, darkness. 2 beams of light, added together, can make blackness. Bullets cannot do that. No matter how you fire pellets through 2 gaps, more pellets never produce fewer hits. Light, Young announced, is a wave. He presented this to the Royal Society of London, the institution Newton himself had presided over, and the reception was vicious. One prominent reviewer dismissed the work as containing nothing worthy of the name of experiment, and defended the honour of Newton against this presumptuous physician. But ridicule is not a counter-argument, and the stripes did not go away. Within a generation, the wave theory had conquered. The French engineer Augustin-Jean Fresnel rebuilt it on rigorous mathematics, and his theory survived one of the most theatrical confrontations in scientific history. The mathematician Siméon Poisson, intending to destroy Fresnel, derived from his equations an obviously ridiculous prediction. If light were truly a wave, then in the very centre of the shadow cast by a perfectly round obstacle, there should be a tiny bright spot, light bending around all sides of the disk and reuniting, crest on crest, in the middle of the darkness. Absurd, said Poisson. Then someone did the experiment. The bright spot was there, glowing serenely in the middle of the shadow, and it has been called the Poisson spot ever since, named, a little cruelly, after the man who predicted it in order to mock it. The ray was dead. First, collapse. The wave picture then ascended to something close to perfection. In 1865, the Scottish physicist James Clerk Maxwell completed a set of equations describing electricity and magnetism, 2 phenomena that had seemed like separate curiosities, lodestones and lightning, amber and eels. Maxwell's equations revealed them as 2 faces of a single thing, the electromagnetic field, and the equations contained a surprise. They predicted that a disturbance in this field, a changing electric field, creating a changing magnetic field, creating a changing electric field, could pull itself along through empty space as a self-sustaining wave. The equations even specified this wave's speed, computed purely from 2 constants, measured on laboratory benches with coils and capacitors. The number that came out was about 300 million meters per second. The speed of light was already known by then, from astronomy and from spinning mirror experiments. The 2 numbers matched. Maxwell had been studying electricity, and light fell out of his mathematics. Light is an electromagnetic wave. It remains, in my opinion, the single most beautiful surprise in the history of physics. Maxwell's discovery also blew the doors off the spectrum. If light is an electromagnetic ripple of a certain wavelength, then there should be ripples of every other wavelength too, longer and shorter, above and below the visible. There are radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, all of them light, all of them the same phenomenon at different scales. Most of them discovered in the decades after Maxwell pointed the way. The light your eyes can detect turned out to be a thin slice of an enormous continuum, which you already suspected from Part 2. Let me give the famous speed its proper introduction, because it will matter for the rest of the night. Light in a vacuum travels at 299,792,458 meters per second. Numbers that large mean nothing without an anchor, so here are 3. In 1 second, light could circle the entire Earth about 7.5 times. The light of the moon reaches you about 1.3 seconds after it leaves the lunar surface, so you always see the moon as it was a heartbeat ago. The sunlight warming your face left the sun 8 minutes and 20 seconds earlier. If the sun were somehow deleted from the universe, you would enjoy 8 more minutes of ordinary daylight before you found out. By the late 1800s, physics felt finished. Light was a wave in the electromagnetic field. The equations were exact, and the only loose threads seemed minor. There was that ether problem, admittedly. In 1887, Albert Michelson and Edward Morley built an instrument sensitive enough to detect the Earth's motion through the supposed ether. The medium light waves were said to ripple in, and they found nothing. No ether wind, no medium, no pond under the ripples. Light was a wave that waved in nothing, a fact everyone agreed to find puzzling and almost no one recognized as a warning shot. The experiment itself deserves a sentence of admiration, because Michelson's interferometer compared the speed of light along 2 perpendicular arms, while the Earth swung around the Sun at 30 kilometers per second, and it was sensitive enough to detect a difference of 1 part in 100 million. The Earth's motion should have produced an ether breeze along one arm, and the instrument was easily good enough to feel it. It felt nothing, in every season, in every orientation, year after year. The null result is sometimes called the most famous failed experiment in history, which is unfair to it. It succeeded perfectly at measuring the truth. The truth was simply unacceptable. The great Lord Kelvin, surveying physics around the turn of the century, is remembered for declaring the subject nearly complete except for 2 small clouds on the horizon. One of those clouds was the puzzle of how warm objects radiate their light and heat. It seemed like a mopping up exercise. It was instead the end of the world as physics knew it. Because the wave picture of light, perfect, confirmed, complete, had about 40 years left to live, and the thing that killed it was nothing more exotic than a glowing oven. Is less than break time equals 1s. Is greater than number. Part 4. The particle returns from the dead. Every warm object glows. You glow, right now, in infrared light your eyes cannot see, about as brightly as a household light bulb in that part of the spectrum. A blacksmith's iron glows dull red, then orange, then yellow-white as it heats, and by the 1890s physicists could measure those glows with great precision. They could not, however, explain them. When they applied the perfected wave theory of light to a simple hot object, the mathematics made a prediction that was not just wrong but deranged. The theory said that any warm body should radiate more and more energy at shorter and shorter wavelengths, without limit, so that your fireplace should be flooding the room with ultraviolet, then X-rays, then gamma rays, an infinite blaze from every ember. Physicists came to call this absurdity the ultraviolet catastrophe, Reality, obviously, declines to behave this way, and the question was why. The answer arrived in 1900 from a conservative, reluctant German physicist named Max Planck, and he hated it. Planck found that he could match the measured glow of warm objects perfectly, but only by inserting an assumption that violated everything the wave picture stood for. He had to suppose that energy is not exchanged between matter and light in a smooth, continuous flow, the way a wave should deliver it, but only in discrete packets, individual parcels, whose size depends on the frequency of the light. He called a packet a quantum, from the Latin for how much. The energy of one quantum equals the frequency of the light multiplied by a tiny constant of nature, now called Planck's constant. Planck regarded this as a mathematical trick, a temporary scaffold to be dismantled once someone found the real explanation. He spent years trying to dismantle it himself. He never managed it because the scaffold was the building. Planck later described the move as an act of desperation, and the phrase tells you everything about the temperament of the man who accidentally started the quantum revolution. He was no rebel. He was a meticulous, dutiful professor who revered the classical physics he was about to wound, and who had once been advised, as a student, not to bother with physics at all, because everything important had already been discovered. When his own equation forced graininess upon the smooth world of waves, he treated the graininess as a stain to be scrubbed out later. The constant he introduced, now written as h, turned out to be one of the foundation stones of reality, a number that sets the scale at which the universe stops being smooth. It is fantastically small, about 6,500 billionths of a joule second, which is why the graininess of light is invisible at the scale of lamps and sunsets. The lumps are simply too fine for human senses to resolve, like the dots of a printed photograph viewed from across a room. It took a glowing oven and a stubborn equation for anyone to notice the dots at all. The word photon, incidentally, arrived late to its own story. Einstein himself spoke of light quanta, and the name photon was only coined in 1926 by the chemist Gilbert Lewis, who, in a final twist of irony, attached it to a theory of his own that turned out to be wrong. The name outlived the theory and was adopted by everyone, which seems fitting for tonight's subject. Even the word for light's particle is a label that drifted free of its original meaning and settled on something nobody fully understood. It took a 26-year-old patent clerk to say so out loud. In 1905, Albert Einstein published a paper arguing that Planck's packets were not bookkeeping but reality. Light itself, Einstein proposed, is grainy. It travels as discrete lumps of energy, and a beam of light is a swarm of them. His evidence was a small laboratory puzzle called the photoelectric effect. Shine light on a metal surface, and under the right conditions, electrons pop out. The wave theory made clear predictions about this. A brighter wave carries more energy, so brighter light should eject faster electrons, and any color of light, given time to slosh enough energy in, should eventually shake some electrons loose. The laboratory said no to both. Red light, below a certain threshold frequency, ejected nothing, no matter how blinding its brightness or how long it shone. Faint violet light, above the threshold, ejected electrons instantly, with not even a billionth of a second of delay. Brightness changed, only how many electrons came out, never how fast they flew. Frequency, the color, controlled everything about their energy. Einstein's lumps explained all of it in one stroke. If light arrives as individual packets, and each packet's energy depends only on frequency, then a single red packet simply does not carry enough energy to kick an electron free, and a million weak packets cannot pool their resources because each electron absorbs them one at a time. A violet packet carries plenty, so even sparse violet light works immediately. Brightness is the number of packets. Color is the energy per packet. The particle of light executed by Thomas Young a century earlier, had climbed out of its grave. We now call Einstein's packet the photon, and this, not relativity, is what won him the Nobel Prize in 1921. The committee, nervous about relativity's bold strangeness, cited the photoelectric effect. There is a certain comedy in that, because the photon turned out to be far stranger than anything relativity ever proposed. Confirmation kept arriving. In 1923, the American physicist Arthur Compton fired X-rays at electrons and watched the light bounce off them exactly the way one billiard ball bounces off another, transferring momentum, changing direction, losing a precise and predictable amount of energy in the collision. Waves do not do that. Projectiles do. When light hits matter, it hits like a thing, a countable, colliding thing. And so physics arrived at an open scandal. Interference. The stripes of Part 3 proved beyond doubt that light is a wave. The photoelectric effect and Compton's collisions proved beyond doubt that light is a stream of particles. Both sets of experiments were airtight. Both were repeated, refined, and confirmed, and they flatly contradict each other. A wave is spread out, continuous, divisible, capable of cancelling itself into darkness. A particle is compact, discrete, indivisible, and arithmetic forbids more particles from adding up to fewer arrivals. The second collapse had happened. Light was not the wave physics had settled on, and it could not simply go back to being Newton's bullets either, because the stripes still glowed on every screen. Light was somehow both, which is to say, it was officially neither, and nobody could say what it actually was. It is worth pausing on how much this tormented the very people who discovered it. Einstein wrote, decades later, that 50 years of conscious brooding had brought him no closer to answering the question, what are light quanta? He added, with visible irritation, that nowadays every rascal believes he knows the answer, but he is deluding himself. Hold on to that sentence tonight. The man who discovered the photon went to his grave declaring that he did not know what it was. Whatever you fail to understand in the next 2 hours, you fail in extraordinary company. The truce that physics negotiated was called wave-particle duality, and the Danish physicist Niels Bohr gave the truce its constitution. He named the principle complementarity. Wave and particle, Bohr said, are two complementary faces of light, and no experiment will ever show you both at once. Ask a wave question with slits and screens, and light answers as a wave. Ask a particle question with counters and collisions, and light answers as a particle. The two descriptions never collide head-on, because the experimental arrangements that reveal them are mutually exclusive. To Bohr, this was not a compromise, but a discovery about reality itself. To Einstein, it was surrender, dressed up as philosophy, and he spent years inventing brilliant thought experiments designed to catch light, displaying both faces at once to prove the fuzziness was in our knowledge rather than in the world. At a famous series of conferences in the late 1920s, Einstein would arrive at breakfast with a new trap, and Bohr would return by dinner, having found the flaw. Bohr won every round, but always on paper. The technology to actually run their duels did not exist and would not exist for nearly a century. Remember that detail. It is the fuse that leads to MIT. In the meantime, working physicists settled into the unhappy peace. They used wave equations when designing lenses and antennas, particle pictures when calculating collisions, and they trained generations of students to switch between the two without asking embarrassing questions at parties. The arrangement worked magnificently and explained nothing, because the obvious question was still sitting there, untouched, almost too simple to take seriously. Light is supposedly emitted and absorbed as individual, indivisible photons. The stripes are supposedly built by waves passing through two slits and cancelling. So what happens if you turn the brightness down until only one single photon is in flight at a time, and send it toward the two slits alone. A lump must surely pick a slit, mustn't it? Is less than break time equals 1s is greater than number, part 5, 1 photon at a time. Picture the experiment with me, slowly, because it deserves an unhurried telling. A light source sits at one end of a dark enclosure, dialed down to almost nothing. It is so faint that photons leave it one at a time, with long, lonely gaps between them, and at any given moment there is at most one photon traversing the apparatus. Each photon, by everything Part 4 established, is an indivisible lump. Ahead of it stands the barrier with its two narrow slits, and beyond that, a detection screen sensitive enough to register a single arrival as a single small dot. Then you do the one thing physics is best at. You wait and you count. The first observations behave themselves. A photon departs, and a moment later, a single dot appears on the screen. One photon, one dot, one definite arrival at one definite place. That is particle behavior, exactly as advertised, and nothing about a lone dot looks mysterious. The dots land here and there with no obvious order, like the first raindrops on a dry sidewalk, and if you stopped at a dozen photons, you would conclude that nothing interesting was happening. So you do not stop. You send the next photon only after the previous one has finished its journey. Hundreds, then thousands, then tens of thousands of solitary travellers, each one crossing the apparatus utterly alone, with nothing to interfere with except, perhaps, itself. And the stripes assemble, out of the random-seeming scatter of dots. Slowly, undeniably, the interference pattern emerges. Bright bands where dots crowd together, dark bands where no photon ever lands. The pattern is identical to the one Young saw with full sunlight, but there is no second wave here to cross with the first, no crowd of light overlapping in the slits. Each photon travelled by itself. Each photon arrived as one dot, and yet the dots, collectively, respect a wave pattern that requires passing through both slits at once. The dark bands are the truly damning part. There are places on that screen a photon can reach easily when one slit is open, and can no longer reach when the second slit is opened. Adding a route removes destinations. No bullet, no pellet, no lump that takes one path or the other can behave this way. This is not a modern stunt, by the way. The first version was run in 1909 by a young man named Jeffrey Ingram Taylor, who dimmed his light source to the equivalent of a candle burning more than a mile away and aimed it at a needle's shadow. His exposures ran for up to 3 months, photons trickling through one at a time onto a photographic plate while he, by some accounts, went sailing. When he developed the plates, the interference fringes were there, soft and patient and impossible. The result has since been repeated with equipment Taylor could not have dreamed of, and the pattern always comes. It is worth dwelling on what the phrase interferes with itself is being asked to carry here, because it is doing impossible work, and noticing the impossibility is the whole lesson. For interference, you need two waves meeting, crest against crest, crest against trough. With one photon in the apparatus, what are the two parties? The mathematics of quantum theory answers without embarrassment. The photon is described by a wave of possibility that passes through both slits, and the two branches of that possibility recombine on the far side, reinforcing here, cancelling there, sculpting the odds of where the single dot will land. The mathematics works flawlessly, every time, to as many decimal places as anyone has ever checked. What nobody can supply is the picture, the story of what is physically wading through those slits. A possibility is not a thing, and yet possibilities, in this universe, apparently cancel each other out the way colliding ripples do, and leave dark stripes on real screens where real photons refuse to land. The dots themselves are worth a moment of quiet appreciation too. In Tonomura's electron version of the experiment, the team recorded the arrivals on video, and you can watch the footage today. For the first 100 dots, there is nothing, pure scatter, static on a screen. At 1,000 dots, there is a faint ribbing, the kind of thing you would dismiss as imagination. At 70,000 dots, undeniable, elegant stripes. No single arrival knows anything about stripes. Each electron, like each photon, lands exactly once, alone, having interfered with nothing visible. The pattern lives only in the statistics, the way a portrait lives in the dots of a newspaper photograph, except that here no editor arranged the dots. The arrangement seeps in from somewhere outside the story we can tell. So you ask the obvious next question, the one every student asks, the one you are probably asking right now. Fine. Which slit did the photon actually go through? You rig a detector at the slits, some gentle sensor that notes the passage, left or right, and you run the experiment again. The detector works. It dutifully reports a slit for every photon, left, right, right, left, each one a definite answer. And on the screen behind, the stripes are gone, vanished. In their place, two plain heaps of dots, one behind each slit, exactly the stencil spray pattern Newton's bullets would have made. Remove the detector, run it again, and the stripes return. Whether light behaves as a wave or as a particle depends on whether the apparatus is capable of knowing which path it took. I want to be careful here, because this is the point where popular accounts often reach for spooky words. It is not that the photon notices a human watching and shyly changes its behavior. Consciousness has nothing to do with it. The experiments are crisp on this point. What matters is whether the path information exists anywhere in the universe, recorded in anything, a detector's memory, the recoil of an atom, a single stray molecule that bumped the photon and carries the answer off in its motion. If the information exists, the pattern dies. If it does not, the pattern lives. The universe behaves as though it is keeping accounts, and the currency is information. You should find that more unsettling than the spooky version, not less. And in Part 6, a team in Massachusetts is going to weigh that currency on a scale. The strangeness also refuses to stay confined to light. Matter does it too. Electrons, fired one at a time through a double slit, build the same stripes, a result confirmed beautifully in the Japanese physicist Akira Tonomura's 1989 experiment, which recorded the pattern assembling electron by lonely electron, and which physicists later voted the most beautiful experiment in history. Neutrons do it, whole atoms do it. By 2019, researchers in Vienna, led by Marcus Arndt, had sent molecules of roughly 2,000 atoms, lumpy objects heavier than 25,000 hydrogen atoms put together, through an interferometer, and the stripes still formed. Every particle of matter is apparently infected with the same double nature as light. The disease Young discovered in 1801 turns out to afflict everything that exists. Richard Feynman, who understood quantum mechanics as well as anyone who has ever lived, told his students that this experiment contains the only mystery, that every other quantum puzzle is this one wearing a different coat, and that nobody, himself included, could explain it in terms of anything more familiar. His advice was to absorb the experimental facts directly, because the facts are the bedrock. So let me state the facts at their starkest. Between the source and the screen, the photon has no trajectory. It does not sneak through the left slit nor the right, nor both in the way a wide wave straddles a rock, nor neither. Every one of those stories, taken seriously, predicts something the experiments refute. The honest statement is that the photon in flight has no position, no path, and no story. Asking where it was between emission and arrival is like asking what your lap looks like when you stand up. The question has the grammar of sense and none of the substance. By the middle of the 20th century, this was the third collapse, and it was the strangest one yet. Light is not a wave. Light is not a particle. Light is not a diplomatic mixture of the two. Light is something for which human language has no noun, a something that shows definite faces only when asked definite questions. But one refuge remained for common sense, and Einstein occupied it for the rest of his life. Perhaps, he argued, the photon does have a definite path, and quantum mechanics is simply incomplete, blind to hidden details. Perhaps the act of detecting the path physically jostles the photon, smearing out stripes that would otherwise have formed. A disturbance story, a loophole. Closing it would require an experiment of almost impossible purity, where the slits themselves are single atoms whose knowledge can be tuned like a dimmer switch, and where no clumsy mechanism can be blamed for anything. That experiment took 100 years to become possible. It was finished in July of 2025. Those less than break time equals 1s is greater than number, part 6, MIT, 2025, the cleanest cut. The coldest places in the known universe are not in space. They are in laboratories, and one of them is in Cambridge, Massachusetts, at the MIT Harvard Center for Ultra-Cold Atoms. There, Wolfgang Ketterle and his colleagues work with clouds of atoms chilled to a few billionths of a degree above absolute zero, colder than the gaps between galaxies by a factor of about 1 billion. Such cold is not the goal for its own sake. Cold means slow, and slow means controllable. At those temperatures, atoms stop being a frantic blur and become things you can hold, arrange, and prepare in chosen quantum states, almost one by one. Ketterle won the Nobel Prize in 2001 for using such cold to create a new state of matter. A quarter century later, his team used it to put the oldest question in optics on trial. Here was the design. The team cooled more than 10,000 atoms and loaded them into a lattice of crossed laser beams, an egg crate of light that holds each atom in its own gentle pocket, spaced out in a regular array. Each atom would play the role of a slit, not a metaphorical slit, a functional one. Shine weak light on 2 neighboring atoms, and each atom scatters a little of it, becoming a tiny source of outgoing ripples, exactly as the openings in Young's barrier were. If the ripples from the 2 atoms overlap and interfere, you get fringes. If they do not, you get none. And the light was made deliberately feeble, so weak that each atom would scatter at most a single photon. 1 photon, 2 atoms, and empty space. Every plank, every barrier, every mechanical excuse stripped away. The double-slit experiment reduced to its quantum skeleton. The crucial innovation was the dial. An atom held in a laser pocket is itself a quantum object, and it can be prepared tightly or loosely, pinned or fuzzy. A tightly pinned atom barely moves when a photon glances off it, which means the atom keeps almost no record of the encounter. A loosely held, fuzzy atom recoils in a way that correlates with the photon's path, which means the atom does keep a record, a faint memory written into its motion, readable, in principle, by anyone who interrogated the atom later. By adjusting the laser trap, the team could choose precisely how much which path information each scattering event would deposit in the world, not whether a detector clicked, not whether a human looked, simply whether the information would exist. Let me unpack that word fuzzy, because the whole experiment turns on it, and it rewards a slow look. An atom held in a pocket of laser light is not sitting at a point the way a marble sits in a bowl. Quantum mechanics forbids that. The atom occupies a small cloud of possible positions, and the size of that cloud is adjustable. Squeeze the trap tight, and the cloud shrinks. But by the uncertainty principle, the atom's motion becomes wilder and less predictable, so a photon's tiny kick disappears into noise the atom was already making. The encounter leaves no legible record. Loosen the trap and the cloud spreads. The atom's motion calms, and now the kick from a passing photon stands out, a clean fingerprint pressed into the atom's state. The dial on the MIT experiment was, in essence, a dial controlling how good a witness each atom would be. The photons never knew the difference, if knowing is even a word we are allowed anymore. The light arriving at the atoms was identical in every run. Only the quality of the witnesses changed, and the wave pattern lived or died accordingly. There is also a lovely historical symmetry in who performed this experiment. The debate it settles was conducted in the 1920s at the Solvay conferences in Brussels, in dining rooms and hotel corridors, between men arguing over apparatus that could not be built. Einstein kept proposing mechanical contraptions, shutters, springs, recoiling slits, each designed to catch light wearing both faces. Bohr kept finding that the contraption's own quantum nature would always blur the result just enough to protect the rule. Neither man could test anything. They were fencing with imaginary equipment over the nature of reality, and the match was scored on logic alone. It took 100 years, the invention of laser cooling, the achievement of temperatures colder than anything that occurs naturally in the universe, and a Nobel laureate's laboratory to finally build the imaginary equipment. When the fencing match was replayed with real steel, every touch landed exactly where Bohr said it would. You already know what happened because the whole night has been building to it, but the precision is the point. When the atoms kept no record, the scattered light produced clear interference, the wave face of light, fringes plain and strong. As the team turned the dial, letting the atoms record more and more about the photon's path, the fringes faded, smoothly and predictably, in exact lockstep with the amount of information available. More path information, less wave. Full path information, no wave at all. The trade-off matched the predictions of quantum theory across the whole range of the dial, with nothing left over and nothing unexplained. The result was published in Physical Review Letters on July 22, 2025. Now recall Einstein's last refuge from Part 5, the disturbance story, the hope that measuring the path physically kicks the photon and smears the stripes. The MIT experiment was built to demolish exactly that hope, and it included a wonderfully direct touch. In the 1920s, Einstein had imagined hanging a slit on springs, so that a passing photon would nudge it measurably, recording the path mechanically. Bohr had argued back that the spring's own quantum fuzziness would always blur exactly enough to protect complementarity. A century later, the MIT team effectively built the springs and then went one better. In some runs, they released the trap entirely, switching off the lasers so the atoms floated free with nothing holding them, no mechanism present to push back on anything. The trade-off did not budge. The fringes cared about one thing only, the fuzziness of the atom's quantum state, the information it carried. Not forces, not jostling, not machinery. The loss of the wave is not a mechanical injury inflicted by clumsy instruments. It is an informational fact about the universe. That sentence is the load-bearing disturbance of this entire video, so let me say it once more, slowly. Light loses its wave nature, not when something touches it, but when something, anything, knows its path. It is worth appreciating how strange that is, compared to every ordinary fact you know. A bell rings the same whether or not anyone records it. A thrown stone lands in the same spot whether or not a camera tracks its arc. Information about ordinary things is a bystander. Information about quantum things is a participant. The universe behaved, in that Massachusetts basement, as though the existence of an answer, anywhere, in anything, is itself a physical force shaping what light can do. The atoms were never read out. Nobody checked their memories. The mere fact that the memory existed was enough to kill the fringes. The universe keeps its own books, and it balances them whether or not anyone audits. And notice what this verdict does to the precision pedestal we put physics on. The theory vindicated here, quantum mechanics, is not some speculative sketch. Its extension, quantum electrodynamics, predicts the magnetic behavior of the electron correctly to about 1 part in a trillion, which is like measuring the distance from New York to Los Angeles to within the width of a human hair. That theory, the most accurate instrument of thought our species has ever built, is the same theory that insists light has no independent nature. The accuracy and the strangeness come as a package. You cannot keep the lasers and the satellites and the medical scanners while quietly returning the part where reality declines to be definite. It is one fabric. So the 100-year argument has its answer, as clean as it will ever come. Einstein believed light must be something in itself, with the fuzziness living in our ignorance. Bohr believed light has no face until a question selects one. The cleanest cut ever made, says Bohr. Light shows you the face your question chooses, and there was never a face underneath. Settle into that thought without fighting it, the way you would settle into a strange but comfortable chair. It has now been measured. It is no longer philosophy. You might reasonably hope that this is as strange as light gets, that at least outside the quantum laboratory, in the open air of relativity, light behaves like a respectable traveller with a respectable itinerary. It does not. Long before MIT, Einstein's own earlier triumph, the theory everyone celebrates him for, had already revealed something about light that may be stranger than anything complementarity ever claimed. Ask what a journey is like from light's own point of view, and physics returns an answer that should not be read late at night, except that here we are. The answer is that there is no journey, no time, and no point of view at all. Is less than break time equals 1s. Is greater than number. Number, part 7. The thing with no clock. Set the slits aside for a while. Forget interference, forget detectors, forget information. We are going to spend this part entirely inside Einstein's relativity, the physics of space and time themselves, and we are going to ask one innocent question. What is it like to be light? The answer requires a little preparation, but I promise the preparation is gentle and the destination is worth it. Begin with the speed. 299,792,458 meters per second. That number is now exact, and not because our instruments achieve perfection. In 1983, the International Committee that governs measurement made a quietly profound decision. They defined the meter as the distance light travels in a vacuum in 299,792,458th of a second. Read that carefully and you will see the inversion. We no longer measure the speed of light using our standard of distance. We define our standard of distance using light. Light is no longer measured against the world. The world is measured against light. Human civilization, without much fanfare, rebuilt its rulers on the assumption that light is the most reliable thing in the universe. What earned light that trust is the strangest experimental fact of the early 20th century. The speed of light in a vacuum is the same for every observer, no matter how they move. Chase a beam of light at 99% of light speed, measure how fast it recedes from you, and you get the full value, as though you were standing still. Race toward a light source, and its light approaches you at exactly the same speed, not a whisper faster. This is flatly impossible for anything else. Drive toward an oncoming car, and your speeds add. Drive toward an oncoming light beam, and they refuse to. Every experiment ever performed confirms it, and Einstein's genius in 1905 was to stop treating it as a paradox to be explained away and start treating it as a law to build on. If the speed of light is fixed for everyone, he reasoned, then something else must give. The things that give are space and time themselves. Here is the gentlest way I know to see it. Imagine a clock made of light, two mirrors facing each other, a single pulse bouncing between them, each bounce one tick. Now let that clock fly past you at enormous speed. From your point of view, the pulse no longer bounces straight up and down. It traces long diagonals, because the mirrors are moving sideways while the pulse travels. Diagonals are longer than verticals, and the pulse cannot speed up to compensate because light's speed is locked. So, from your point of view, each tick takes longer. The moving clock runs slow, and the disturbing discovery of relativity is that this is not a quirk of light clocks. All clocks slow identically, mechanical, biological, atomic, because time itself runs slower for the mover. This is not theory in the loose sense. The atomic clocks aboard GPS satellites tick measurably differently from clocks on the ground, and your phone's map corrects for it every time it places you on the correct street. The faster the motion, the stronger the effect, and the relationship is not linear but runaway. At 10% of light speed, time dilation is a rounding error. At 90%, time runs at less than half pace. At 99.99%, a traveller ages 1 year while 70 pass at home. Push closer and closer to the speed of light, and the slowdown grows without bound. And now follow the curve all the way to its end, to light speed itself. The mathematics is unambiguous about the limit. At the speed of light, elapsed time is 0. Not small, 0. A photon is the only traveller that actually lives at that limit. So take the thought seriously and trace a real journey. A photon is emitted from a galaxy 10 billion light-years away. From our perspective, it crosses the cosmos for 10 billion years, threading past galaxy clusters, outliving stars, before it finally buries itself in your retina some night when you happen to glance up. From the photon's own accounting, the elapsed time between emission and absorption is 0. No seconds, no instants, nothing. And the strangeness doubles, because relativity pairs time dilation with length contraction. Distances compress along the direction of travel, and at the speed of light, the compression is total. The 10 billion light-years shrink to no distance at all. From the limit of the photon's frame, the surface of that ancient galaxy and the inside of your eye are not separated by an epic journey. They touch. Departure and arrival are a single event, one instantaneous contact between 2 points the universe insists are 10 billion light-years apart. Now, I owe you an honest correction, and it is the kind of correction that makes things stranger rather than safer. A physicist will tell you, properly, that the photon does not have a point of view. Relativity is built on comparing perspectives of observers moving slower than light, and its equations simply cannot be occupied at light speed. The photon's frame is not a forbidden room. It is a room that does not exist. So, the rigorous statement is not that the photon experiences 0 time, it is that the photon does not have experiences, a clock, a biography, or a perspective at all. The question, what is it like to be light, is not unanswered. It is unaskable. And notice what that does to our thread. All night, we have been cataloguing the things light fails to have. No fixed face. No path through the slits. Now relativity adds its own entries to the inventory. No clock, no distance, no point of view. Light is not a thing that endures through time the way you do, persisting from moment to moment. It is something more like a connection between two events, a seam in space-time, and every property we naively assign to its journey belongs to us, the slow ones, watching from outside. The reason light lives at this extreme is mass, or rather the lack of it. The photon is massless, and in relativity, masslessness is not a deficiency, but a mandate. Anything with 0 rest mass must travel at exactly the speed of light, always, with no option to slow down, and anything with mass can never quite reach that speed. A photon has never accelerated. It did not depart its galaxy sluggishly and work up to speed. It was born at the only speed it is permitted to have, and it will be extinguished at that same speed. There are no resting photons anywhere in the universe, and there never have been. Experimentalists who trust nothing have checked If the photon secretly had even a wisp of mass, the consequences would be measurable. Far-away radio waves would lag behind far-away gamma rays, and the static fields of planets would warp in telltale ways. The current experimental ceiling puts any photon mass below roughly 10 to the minus 54 kilograms. For comparison, an electron, itself absurdly light, weighs in at about 9 times 10 to the minus 31 kilograms. If the photon weighs anything at all, it is at least 1,000,000,000,000,000 times lighter than the lightest matter we know, and the standard theory simply books it as zero. I should mention, in fairness, that light's famous speed does come with fine print, and the fine print is delightful. In 1999, the Danish physicist Lene Howe and her team at Harvard sent a pulse of laser light into a cloud of sodium atoms cooled into a single collective quantum state, and slowed that pulse to 38 miles per hour. A cyclist with strong legs could have outrun it. 2 years later, her group brought a pulse to a complete stop, parked its information in the atoms, and then revived it on demand. By 2007, they could stop light in one cloud, carry its imprint across a gap inside a sliver of matter, and re-emit the same pulse from a different cloud entirely. None of this violates relativity, and the reason is the thread of this whole video. Inside a medium, what propagates is not a bare photon, but a joint excitation of light and matter wearing each other, and the joint thing can dawdle. The sacred constant describes light in nothing. Even the speed of light, the one fact about light everybody knows, turns out to be a statement with an asterisk, true of the vacuum, negotiable everywhere else. The comfortable certainties keep acquiring fine print the closer we look, which by now should feel familiar. And since we are filing honest footnotes, here is one about the sunlight on your face. The light you see left the sun 8 minutes and 20 seconds ago, but that is only the last leg of its story. The energy in that light was released by fusion in the sun's core, and the core of a star is so dense that light cannot cross it freely. The energy staggers outward in a blind random walk, absorbed and re-emitted endlessly, covering on the order of 100,000 years just to reach the surface. The glow warming your skin on any afternoon is, on the inside, older than human civilization, and, on the outside, 8 minutes old. Even sunlight, the most ordinary light there is, carries a secret age. One more property belongs in this part, because it completes the portrait of the traveller with no clock. Photons do not age, but the universe edits them in transit. Space itself has been expanding for 13.8 billion years, and as it expands, it stretches the wavelengths of the light travelling through it. Astronomers call this redshift. The oldest light in the universe began as the orange-white glow of a young cosmos at around 3,000 degrees, and after 13.8 billion years of stretching, it arrives today as a faint microwave hiss at 2.7 degrees above absolute zero. The photons never aged a second of their own. The road itself lengthened beneath them and retuned them as they flew. Where the lost energy goes is a question that makes even professionals shift in their chairs, because energy, in an expanding universe, is not globally conserved in the comfortable way schoolbooks imply. So here is the inventory as it now stands, the dossier on the universe's most trusted messenger. No fixed face, only the one your question selects. No path between the slits, no clock, no distance, no point of view. An exact speed in nothing, an adjustable speed in something, and a wavelength the cosmos quietly retunes in flight. You would be forgiven for hoping the strangeness is at least finished accumulating. It is not, because physicists in the 20th century found a way to sharpen the double slit into something crueler. They asked what happens if you wait until the light has already committed, until its journey is over and done, and only then choose which question to ask it. The experiment is called delayed choice. At first reading, it appears to show your decision tonight reaching backward and rewriting what a photon was doing billions of years ago. The truth is more careful than that, and, I think, more unsettling. That is where we go next. Is less than break time equals 1s is greater than number, part 8. Delayed choice. The universe waits for your question. Everything we have established tonight converges on one brutal question. If light has no definite nature until a measurement selects one, and the MIT experiment says exactly that, then when does the selection happen? At the slits? At the screen? Somewhere in between? The American physicist John Archibald Wheeler, a man who mentored Richard Feynman and named the black hole, spent years sharpening this question into an experiment, and his answer to when is the reason this part exists. The selection can be forced after the journey is over. You can choose your question once the light has, by any classical reckoning, already finished answering a different one. Here is Wheeler's idea in its cleanest form. Send a photon toward the familiar two slits. Beyond them, you have two options for receiving it. Option 1 is the screen, which collects the interference pattern, the wave answer. Option 2 is a pair of tightly aimed telescopes, each focused on one slit, which would tell you which slit the photon came through, the particle answer. Now the twist that earns the name delayed choice. You wait. You let the photon pass the slits first, while the screen is in place, and only then, in the last sliver of its flight, you decide whether to leave the screen or snatch it away and let the telescopes look. The photon committed at the slits, so the classical story goes, either spreading like a wave through both or threading like a particle through one. Your late decision should be too late to matter. It is not. Run the experiment, and the statistics obey your final choice, not the photon's supposed earlier commitment. Choose the screen late, and you find wave behavior. Choose the telescopes late, and you find clean particle paths. This is not a thought experiment anymore. A French team, under Alain Aspect, performed a rigorous version in 2007, randomizing the choice with a quantum dice roll, while each photon was already in flight inside the apparatus. The results matched quantum theory perfectly, as they always do. Wheeler, who had a gift for the cosmic flourish, pointed out that nature has built this experiment at a scale no laboratory could fund. Take a quasar, billions of light years away, whose light passes a massive galaxy en route to Earth. The galaxy's gravity bends the light, so the quasar's glow can reach us by two routes, around the left side or around the right. Two paths. A double slit the size of a galaxy. Point your telescope tonight, and you may choose how to combine that light, asking the wave question or the particle question of photons that began their journey billions of years before the Earth existed. Your choice, made over a cup of tea, appears to determine whether each photon travelled one path or both for the entire duration of a journey that ended this evening and began before there were oceans. Wheeler put the moral in one of the most quoted sentences in physics. No phenomenon is a real phenomenon until it is an observed phenomenon. Put some numbers on that cosmic version, because the scale is the argument. The lensing systems Wheeler had in mind involve quasars whose light has travelled for 8 or 10 billion years, more than half the age of the universe. The galaxy doing the bending might sit billions of light years out, splitting the light into paths that differ in length, so that one image of the quasar is actually older than its twin by months or years. Photons from such a system are arriving at Earth continuously, tonight included. Each one, on the classical story, must have committed long ago to travelling the left route around the galaxy, or the right, or somehow both. The commitment would have been made before the sun ignited, before the Milky Way settled into its current spiral, before there was any planet here to receive it. And yet the formalism of quantum mechanics, backed by every laboratory test of delayed choice, insists that the question of one path or both has no answer until the receiving apparatus defines it, this evening, on a mountaintop in Chile, or a desert in Arizona. The interval between the supposed decision and the question is 10 billion years, and the physics shrugs at the gap as though it were nothing, because to the photon, as Part 7 taught us, it is nothing. Then physicists built something even more provocative, the delayed choice quantum eraser. In this version, each photon gets tagged at the slits, marked in a way that records its path without blocking it, and the tag predictably kills the interference. The pattern on the screen shows no stripes, but the tag can be erased downstream, after the photon has already landed, by measuring its entangled partner in a way that scrambles the path record forever. And when experimenters do that, then sort the screen's dots according to the partner measurements, the stripes reappear within the sorted groups. Erase the information after the fact, and wave behavior seems to return after the fact. The headlines write themselves, and they have for 25 years. The present rewrites the past. The future reaches back. Measurement tonight changes what light was doing last week. I need to be honest with you now, the way I promised to be all night, because the sober reading of these experiments is different from the headlines, and most working physicists hold the sober reading. Nothing reaches backward in time. Watch the raw data carefully. In the eraser experiment, the screen itself never shows stripes. Never. The raw pattern is always the plain, stripeless smear, no matter what anyone erases later. The stripes appear only when you take the complete record and sort the dots into groups using the partner measurements after everything is over. One group shows stripes leaning one way, another group stripes leaning the other, and the groups interleave so perfectly that together they add up to the featureless smear that was always there. Nothing about the past changes. What changes is which subset of the past you are looking at. The technical name is post-selection, and recent careful analyses, including work published as recently as 2025, keep reaching the same verdict. The eraser is a sorting phenomenon, not a time machine. Sean Carroll, the physicist and writer, has made a sport of patiently explaining this, and he is right. A homely analogy may help the sorting idea land, though, like all analogies tonight, it will limp. Imagine a casino that mails you a record of 1,000 roulette spins, an apparently patternless list of reds and blacks. Later, a second envelope arrives, containing 1,000 notes from the croupier, one per spin. When you sort the spins into 2 piles according to the croupier's notes, each pile shows a beautiful regularity that the full list hides. Nothing about the spins changed when the second envelope arrived. The order was in the correlations all along, invisible until you had the key. In the quantum eraser, the screen's dots are the spins, and the partner photons are the croupier's notes, with one crucial difference that keeps the analogy honest. In the casino, the spins secretly had the pattern before sorting. In the quantum case, the MIT result and a century of theory insist there was no secret pattern waiting, no hidden fact of the matter. The correlations are real, the keys are real, and beneath them there is nothing further. The universe hands you envelopes that sort perfectly and declines to say what, if anything, was sorted. You might feel a little deflated by that, as though the magician's trick has been explained and the evening owes you a refund. Hold on though, because here is the part. Ask yourself why nothing reaches back to change what the photon was doing at the slits. The time travel story fails for a simple reason. For the past to be rewritten, there would have to be a definite past to rewrite, a fact of the matter about what the photon was doing, wave or particle, this path or that, and there is no such fact. That is not a gap in our records. It is, after MIT, a measured feature of the world. The photon at the slits was not secretly a wave awaiting your future mercy, nor a particle whose alibi could be amended. It had no identity for the future to alter. The delayed choice does not rewrite light's history. It exposes the fact that light never had one, that the story we call history only condenses around the photon when a question finally lands. Wheeler's cosmic version is not weird because your telescope edits billions of years of travel. It is weird because those billions of years of travel never contained an answer at all, and the universe was apparently under no obligation to manufacture one until you asked. So the disturbing truth has survived its most dramatic test wearing its plainest clothes. No retrocausality, no message to the past, just the same quiet fact. Sharpened, light's properties are not carried through time the way your keys are carried in your pocket. They crystallize at the meeting points, where light and question touch, and between those meetings there is nothing it would be correct to describe. Of course, the moment you say that out loud, an enormous question clears its throat at the back of the room. If the photon has no story between meetings, what is actually out there in the meantime? Something travels, surely. Something interferes. What is the universe doing when nobody has asked it anything? Physics has answers to that question. The trouble, and the next part of our night, is that it has at least 4 of them. They contradict each other completely, and every experiment ever performed agrees with all 4 equally. Is less than break time equals 1s is greater than number, part 9, 4 stories. Physicists tell themselves, the experimental facts of quantum mechanics are not in dispute anywhere on Earth. Every laboratory, on every continent, measuring light with any instrument, gets the same numbers, the same stripes, the same trade-offs, the same flawless agreement with the same equations. What physicists cannot agree on, after a century of unbroken success, is what the equations are about. The argument over what light is, when nobody is asking, has hardened into rival schools, each with its own picture of reality, each fully consistent with every measurement ever made. They are not fringe positions. Each one is held by serious, decorated physicists, and they cannot all be true. Since the double slit is the wound they are all trying to dress, each school is best understood as a strategy for living with what you have heard tonight. The founding strategy is the Copenhagen interpretation, assembled around Niels Bohr in the 1920s, and its answer is bracing. The question, what is the photon doing between measurements, is not hard, it is meaningless. Physics, in this view, is not a description of reality as it exists in itself. It is a calculus for predicting the outcomes of measurements, and the wave function, the mathematical object that interferes through both slits, is a tool of that calculus, not a thing in the world. Asking what light really is, with nobody asking, is like asking what the score of a baseball game is when no game is being played. Generations of physicists were raised on this, often compressed into the only half-joking commandment: shut up and calculate. The strategy works flawlessly. The accusation, pressed by its critics from Einstein onward, is that it is not an answer but a permission slip to stop asking, a do not disturb sign hung on the universe's most interesting door. The second strategy was proposed in 1957 by a doctoral student named Hugh Everett, and it begins with a simple refusal. The equations of quantum mechanics never say that wave functions collapse, that the many possibilities snap into one outcome when measured. Collapse was bolted on to match experience. Everett asked what happens if you delete the bolt and trust the equations all the way. The answer is that every possibility happens. When the photon meets the screen, the universe's quantum state branches, and there is a version of events for every landing spot, each containing its own copy of the apparatus, the laboratory, and you, each copy seeing one definite dot and wondering why. The dot you see does not mark where the photon decided to land. It marks which branch you are in. This is the many worlds interpretation, and its trade is stark. The mathematics becomes the cleanest on offer. No collapse, no special role for observers, nothing but the equations running. The price is an ontology of unimaginable extravagance, a constantly branching reality in which everything that can happen does, somewhere, including endless variant copies of you, some of whom fell asleep several parts ago. The third strategy is the one Einstein would likely have favored, and it descends from ideas of Louis de Broglie in the 1920s, rebuilt by David Bohm in 1952. It is called the pilot wave theory, and it simply refuses to give up the particle. In this picture, the photon is always a real particle with a real, definite position at every instant, no exceptions. It goes through exactly one slit every time, but it is not alone. It rides upon a real, physical wave, and that wave goes through both slits, interferes with itself, and steers the particle, herding it toward the bright bands and away from the dark ones. The stripes assemble dot by dot because each particle has a definite landing place, choreographed by its wave. Everything you saw in Part 5 gets explained with straight realism, definite paths included. The price is paid elsewhere. For the choreography to match experiment, the guiding wave must respond instantly to conditions everywhere, meaning the theory is openly non-local, knit together by influences that ignore distance. Most physicists have judged that price too high. A respected minority pays it gladly and sleeps fine. The fourth strategy is the newest and the most radical about what physics even is. Cubism, short for quantum Bayesianism, says the wave function does not describe the photon at all. It describes you. It is an agent's catalogue of expectations, a betting slip recording what odds a rational gambler should accept on each possible measurement outcome. When the dot appears and the wave function collapses, nothing physical snaps anywhere in the universe. A bet got settled, and the better updated. The strangeness of light, in this view, was never in the light. It was in the awkward fact that we kept mistaking our bookkeeping for the world. What the world is actually like underneath the bets, Cubism leaves pointedly, almost mischievously, open. You might wonder, hearing all this, why the strangeness stays so politely confined, why your bedroom furniture never interferes with itself, and your keys are reliably in one place, given that every atom in them obeys the same quantum rules as the photon. The schools actually share an answer to this one, and it is worth having before sleep. The phenomenon is called decoherence. A quantum object can hold its delicate both paths character only while the universe keeps no record of it, and big warm objects cannot stop making records. Every air molecule that bounces off your keys, every photon of lamplight that scatters from them, every whisper of thermal radiation they emit, carries away information about where they are. A dust grain floating in sunlight is located, in this informational sense, billions of times per second by its environment. The both places possibility is not so much forbidden for large things as instantly confiscated, shredded by an environment that never stops watching. This is the MIT trade-off of Part 6, running wild at full scale. Your world looks solid and definite because it is the most thoroughly measured place in the universe, an arena where everything informs on everything else, ceaselessly. The photon in the double slit is what reality looks like when, for one engineered moment, nothing is taking notes. And the schools are still multiplying, because even the parts of light everyone thought were settled keep reopening. In April of 2025, Gerhard Rempe of the Max Planck Institute of Quantum Optics, one of the most accomplished experimentalists alive, published with colleagues a reinterpretation of interference itself, the phenomenon this entire night has leaned on. When light cancels itself in the dark bands, the textbook says the light is simply not there. Rempe's framework says otherwise. The light enters what he and his colleagues call dark modes, configurations that carry energy but cannot register on detectors, hidden rather than absent. Bright modes are the light that can speak to instruments. Dark modes are light that has gone silent. If that view prevails, then the dark stripes of every double-slit experiment since 1801 are not empty. They are full of light that cannot be seen, and even light's absence becomes a disputed territory. The proposal is new and being argued about, which is exactly the point. In the year 2025, with quantum mechanics a century old, professionals were still publishing rival accounts of what the oldest experiment in optics actually shows. Step back and look at the standoff honestly, because its shape is the disturbing part. 4 pictures of reality. In one, the photon between measurements is a question that should not be asked. In another, it is everything at once, forever, in endless branching copies. In a third, it is a perfectly ordinary particle guided by an extraordinary wave. In a fourth, it is a figure in your private ledger of expectations. These pictures could not contradict each other more thoroughly, and every one of them reproduces every measurement in the history of the science, number for number, stripe for stripe. There is no experiment anyone knows how to perform, even in principle with today's tools, that would crown a winner. The most successful theory our species has ever produced comes with 4 incompatible owner's manuals, and the manufacturer is not answering letters. So our thread reaches a strange completion here, and it is worth saying plainly. The experiments killed every classical picture of light, one by one, ray, wave, particle, truce, and each interpretation is one of 4 incompatible obituaries, 4 attempts to say what it was that died, or whether anything was ever alive in the way we assumed. The disturbing truth about what light really is may not be any particular answer. It may be that the universe declines to owe us one, that what is light, really, is a question reality answers only in the moment of asking, never in general, never in advance, never on the record. Physics can live with that. It calculates beautifully regardless. Whether you can live with it is a more personal matter, and you have all night. But I promised you the edges, and the edges are wilder than the schools. Beyond the 4 respectable stories, there is a frontier of physicists, some decorated, some renegade, who suspect the official account of light is wrong somewhere much more basic. Some doubt the constancy of its speed across cosmic history. Some doubt the expansion story written in its redshift. One school holds that every photon is a handshake, agreed across time, future and past, negotiating each delivery. And one loophole, a century old and genuinely unclosed, concerns whether anyone has ever measured the speed of light at all. That is where we go now, to the heretics. Is less than break time equals 1s, is greater than. Number, Part 10, The Heretics of Light. Every heresy needs an orthodoxy, so let me state the official story of light in one breath. Light is a massless quantum field excitation, travelling through a vacuum at one fixed speed that has held for all cosmic history, the same in every direction, redshifted over billions of years by the expansion of space, and fully described, wherever tested, by quantum field theory. That is the story. Every result tonight has hardened. But a scientific orthodoxy is a structure of load-bearing assumptions, and each assumption is a place where a heretic can set a charge. What follows is a tour of those charges, and I will be careful throughout to tell you which are mainstream curiosities, which are minority science, and which are ideas that survive mostly on the internet. The tour is worth taking even where the heresies fail, because each one illuminates exactly which planks of the official story are proven and which are merely undefeated. Each heretic, you will notice, attacks a different plank. Begin with the loophole that sounds like a conspiracy theory and is, in fact, perfectly respectable. Nobody has ever measured the one-way speed of light. Every measurement ever performed is round trip. We bounce light off a mirror and time the journey out and back, and we divide by 2, and that division hides an assumption. To time a one-way trip, you need synchronized clocks at both ends, and to synchronize distant clocks, you need signals, and the best signals are light, whose one-way speed is the thing you are trying to measure. The circle cannot be broken. Einstein knew this, and was candid that the equal split is a convention, a choice, not a finding. The physicist Hans Reichenbach formalized the point in the 1920s. Light could, in principle, travel at different speeds in different directions, in just the compensating way that keeps every round trip averaging to the famous constant, and no experiment could expose it, because relativity's actual physical content survives untouched either way. To be clear, nothing whatsoever suggests this is so, and the standard convention is overwhelmingly the sensible one. But it is a genuine, century-old, formally unclosable gap between what we say about light and what we have measured, and it sits there, politely, inside every physics textbook on Earth. The most familiar fact about light, that it travels at one famous speed, contains a clause no one can check. If the circularity feels slippery, try to design your way out of it, the way generations of clever students have. Your first instinct is probably to synchronize two clocks side by side, then carry one to the far end of the course. But moving a clock is exactly what relativity punishes. The journey itself desynchronizes the clocks by an amount that depends on the very conventions you are trying to test, and slowing the carry to a crawl does not eliminate the effect, it only matches it perfectly to the assumption you started with. Your second instinct might be a signal other than light, a sound, a bullet, an electrical pulse down a wire. Every one of them is either far too sloppy or, in the case of anything electromagnetic, secretly light again, wearing a costume. Your third instinct, and it is a good one, might be to flash a lamp at the exact midpoint between two detectors and call whatever arrives simultaneous. That is, in fact, precisely Einstein's convention, and it assumes the two-way symmetry rather than testing it. Physicists and philosophers have been auditing proposals like these for a century, and every single scheme, examined closely, smuggles the assumption in through a side door. The loophole is not waiting for a cleverer experimentalist. It is structural, a place where the universe accepts our bookkeeping without ever countersigning it. Now to a genuine minority science heresy aimed at a bigger plank. The official story says light speed has been the same for all of cosmic history. A handful of serious cosmologists have proposed otherwise. In the 1990s, John Moffat and later Andreas Albrecht and João Magejo developed varying speed-of-light cosmologies, in which light travelled enormously faster in the universe's first instance. Their motive was not mischief. The infant universe presents a puzzle. Regions on opposite sides of today's sky have matching temperatures, despite, seemingly, never having had time to exchange anything, light included. The mainstream solution is inflation, a burst of exponential expansion that let a tiny, already equalized patch become the whole visible cosmos. The heretics' alternative is blunt. If light was once vastly faster, the far-flung regions could have spoken directly, and no inflationary burst is needed. The proposal is published, mathematically serious, and testable in principle, since a changing speed of light tends to drag related constants with it, and we can check those constants across cosmic time by reading the light of distant quasars. The verdict from the data so far is cold, and the way we know is its own pleasure to describe. The fine structure constant governs how strongly light and matter grip each other, and it leaves fingerprints in the precise colours that atoms absorb. Astronomers can read those fingerprints in the light of quasars, whose glow has crossed most of cosmic history, comparing atomic physics as it operated 10 billion years ago against atomic physics in the laboratory down the hall. Nature even ran a control experiment for us. 2 billion years ago, in what is now Gabon in West Africa, a uranium deposit at a place called Oklo went critical underground and operated as a natural nuclear reactor for a few 100,000 years, and the isotopes it left behind record the nuclear physics of that era. Quasar light and ancient reactor ash agree. The fine structure constant has held steady to about 1 part in 10 million across billions of years, and any change in the speed of light, large enough to do inflation's job, should have dragged that constant visibly with it. Varying speed of light cosmology is alive in the journals but losing on points, a heresy with credentials and without confirmation. Magejo himself is worth a sentence as a specimen of the breed, because heresy of this caliber requires a particular temperament. He published the varying speed theory while at Imperial College London, wrote a popular book about it whose subtitle described it as a speculation openly relished offending what he called the tyranny of the constant, and accepted that the data would be the judge. That is the difference between a scientific heretic and a crank, and it is the only difference that matters. The heretic states what observation would prove them wrong, and then waits for the observation. The crank explains why every unfavourable observation is part of the conspiracy. By that standard, nearly every figure in this part of our story, whatever you think of their ideas, has been playing the honest game. What it usefully exposes is that the constancy of light speed across all of history is, for the earliest moments, an extrapolation rather than an observation. The next heresy attacks the redshift plank, and it is the zombie of cosmology, dead many times and still walking. In 1929, the astronomer Fritz Zwicky proposed that distant galaxies look redshifted not because space is expanding, but because light gets tired, gradually surrendering energy on its long journey, sagging toward the red. If true, this would dismantle the Big Bang itself, which is why the idea is forever popular with those who would like the Big Bang dismantled. But tired light makes testable predictions, and they fail. If photons wearied en route, distant supernova explosions would not appear stretched in time, yet they do, dimming in graceful slow motion, exactly as expansion predicts. The more distant, the more dilated. A tiring mechanism would also blur distant galaxies and distort the spectrum of the cosmic microwave background away from the flawless thermal curve that satellites have measured to exquisite precision. The blur is absent and the curve is flawless. Tired light is refuted, plainly and repeatedly. I include it for 2 reasons. Its corpse keeps reanimating in internet cosmology debates, so you should recognize its face. And its failure is secretly a triumph of the thread, because the refutation works only because photons do not age or degrade on their own. The light arrives after 10 billion years exactly as strange and exactly as flawless as it departed. Even the heresy that failed certifies the messenger. Now the most philosophically outrageous entry, and my personal favourite for late-night contemplation, because it is aimed not at a measurement, but at time itself. It begins, improbably, with Richard Feynman's doctoral advisor, John Wheeler again, in the 1940s. Wheeler and Feynman developed absorber theory, a reformulation of how light is emitted, in which radiation involves waves travelling forward in time and waves travelling backward in time, from the future absorber to the present emitter, the 2 halves conspiring to produce exactly the ordinary light we see. The mathematics works. In the 1980s, the physicist John Cramer built this into a full reading of quantum mechanics, the transactional interpretation. In Cramer's picture, every quantum event, including every photon that has ever reached your eye, is a transaction, a handshake. The emitter sends an offer wave forward in time. Every potential absorber returns a confirmation wave backward in time, across past and future at once, in a process that does not happen in time at all. One handshake completes, and a photon is exchanged. Atom to retina, star to eye. Each delivery of light is, in this view, an agreement negotiated across the whole interval, the future participating in the past as a matter of routine. It explains the eraser of Part 8 without breaking a sweat, and it reproduces standard quantum predictions, which means experiments cannot currently refute it. It is a minority view, coherent, unfalsified, and unrequired. Mainstream physics has not adopted it, because it buys its elegance with backward causation, and that is a currency most physicists refuse on principle. But notice which plank it questions. Not light's speed, not its aging, but the assumption that light's story must be told forward, from time's heretics to matter's. Among particle physicists, the respectable speculation is the dark photon, and here I must immediately untangle a knot of names. The dark modes in Rempe's 2012 interference work from Part 9 are configurations of ordinary light hidden from detectors. The dark photon is something else entirely, a hypothetical new particle, a shadow twin of the photon belonging to a hidden sector of nature, interacting with our world only through a feeble quantum mixing with ordinary light. The motivation is one of the largest embarrassments in science. Galaxies rotate as though gripped by several times more matter than telescopes can find, and the missing substance, dark matter, has never been directly detected. If a hidden sector of particles exists, a dark photon could be its ambassador, the one portal through which shadow matter whispers to light. Accelerator experiments, including a dedicated program at CERN called NA64, have hunted it for years, firing particles into detectors and combing the debris for the signature of an invisible twin. So far, nothing, only ever-tightening limits on where it could hide. The dark photon remains entirely hypothetical, legitimate, motivated, and undiscovered. Popular headlines occasionally announce that dark photons threaten to upend the double slit or rewrite quantum mechanics. Treat those with a friendly skepticism. The serious version of the idea is quieter and stranger, that the most familiar particle in your life might have a sibling carrying an entire invisible economy, and that the family resemblance is the only way we would ever know. The dark photon also has company in the catalogue of hypothetical light, because physicists have learned to ask one more impertinent question about the photon, namely whether it lives forever. The official answer is yes. A truly massless particle cannot decay, since there is nothing lighter for it to decay into and no rest frame in which to age, which connects back to the missing clock of Part 7. But recall that experiment can only bound the photon's mass, never prove it exactly zero. If the photon carried even the faintest unmeasured mass, decay becomes a formal possibility, and researchers have entertained themselves calculating the limits. The numbers that come out are absurd in the most reassuring way. Given the observed perfection of the cosmic microwave background, which has crossed 13.8 billion years without thinning anomalously, any photon lifetime would have to exceed the current age of the universe by an enormous factor, and that is before accounting for time dilation, which stretches a fast photon's hypothetical fuse almost indefinitely in our frame. Light, in other words, is either perfectly immortal or so close to it that the difference could never matter to anyone. Of all the certainties tonight has dismantled, this one, at least, gets to stay standing, slightly qualified, like everything else light-related, by fine print. And then there is the heresy that is not physics at all, though it borrows physics clothes, and I would be dodging if I skipped it, because after parts 5 through 8, you may have felt its pull yourself. The universe renders on observation. The double slit as a video game optimization, reality-saving computation by leaving the photon's path undrawn until a player looks. The simulation reading. Let me be gentle and clear at once. The emotional logic is understandable, because no definite path, until measured, does sound like deferred rendering. But the analogy dissolves on contact with the actual results. Observation, in every experiment tonight, means physical interaction and information, an atom recoiling, a tag written into a quantum state. It has never meant a mind, a player, or a screen. The MIT result of Part 6 makes the point with precision. The fringes faded according to how much information the atoms carried, with no human in the loop at all, the universe auditing itself. Nothing in the data distinguishes a simulated cosmos from a plain one, which is exactly why simulation talk is metaphysics rather than measurement. And honestly, the real result needs no costume. A universe whose light has no properties until asked is already stranger than a universe that renders on demand. The video game is the tamer story. So ends the tour, and it is worth collecting what the heretics have in common, because together they have quietly drawn us a map. The one-way conventionalists mark the plank no measurement can reach. The varying speed cosmologists mark where constancy is extrapolation. The tired light zombies mark, by their failure, how certified the messenger's fidelity is. The transactionalists mark the unproven assumption that light's story runs only forward. The dark photon hunters mark the possibility that light has invisible kin. Every heresy, the living and the dead, is a bet that light's verified strangeness is a clue to a layer beneath, and every one of them attacks a different unproven plank while leaving the verified strangeness untouched, because it is untouchable. The orthodoxy they besiege is precisely the one the MIT experiment hardened, light with no identity until asked. And here is the quiet thought to carry out of this part. Orthodox or heretical, settled or speculative, every one of these stories is about the same substance, and that substance is not a minor ingredient of the cosmos. By raw count, it is most of what the universe contains. We should spend a little time, before the end, in that ocean. Is less than break time equals 1s, is greater than number part 11. The ocean of unseen light. Count the universe, and light wins. Cosmologists can tally the contents of the cosmos by particle count, and the result reshuffles every intuition about what existence is mostly made of. For every proton or neutron in the universe, every building block of every atom, of every star, planet, and person, there are roughly 1.6 billion photons. The universe is not, by count, a collection of matter with some light moving through it. It is an ocean of light, scattered with traces of matter, and almost none of that light will ever meet an eye, a telescope, or any detector at all. The substance this whole night has failed to pin down is the substance the universe is overwhelmingly made of. Most of that ocean is one specific glow. The cosmic microwave background fills every cubic centimeter of space, everywhere, with about 410 photons. The coffee cup on your nightstand, if you emptied it of everything and held only vacuum, would still contain on the order of 100,000 of these relic photons, passing through on their way from the beginning of time. They were released about 380,000 years after the Big Bang, on the day the universe first became transparent, when the cosmic fog of charged particles cooled into neutral atoms and light was suddenly free to run. It has been running ever since, stretched by expansion from a warm orange glow into a microwave whisper at 2.7 degrees above absolute zero, the oldest light there is, arriving from every direction forever. Your own body intercepts some of it every second of your life. You have been lightly rained on by the Big Bang since the day you were born. The darkness of the night sky, seen against this ocean, becomes a clue rather than an absence. Astronomers of earlier centuries were troubled by a puzzle named for the German astronomer Heinrich Olbers. If the universe were infinite, eternal, and filled with stars, then every line of sight from your eye should eventually end on the surface of some star, and the entire night sky should blaze like the face of the sun. It does not, and the resolution is woven from tonight's themes. The universe is not eternal, so light from sufficiently distant stars has not had time to reach us, and the light that has spent the longest in transit has been stretched by expansion out of the visible range entirely. The darkness between the stars is not empty of light. It is full of light your eyes cannot read, The relic glow we just met shifted into microwaves. When you look at the black gaps in the night sky, you are looking directly at the brightness of the early universe, wearing a disguise of darkness. The sky is not dark. You are just slightly the wrong instrument. That ancient rain is also the reason astronomy works at all. Light's travel time turns every telescope into a time machine, with distance as the dial. Look at the moon, and you see 1 second into the past. The sun, 8 minutes, the nearest stars, years, the Andromeda Galaxy, 2.5 million years. Point a good enough instrument at the right patch of sky, and you read the universe's baby picture, written in photons older than the atoms in your hand. There is no other way to see the past. Light is the only archive the universe keeps, and it keeps it everywhere, unwatched. Even where there are no photons at all, the story does not quite go quiet. Remove every particle of light from a region, and the electromagnetic field remains, humming with irreducible activity that physicists describe as virtual photons, never directly caught, always faintly felt. The hum has measurable muscle. Theory predicted in 1936 that a strong enough magnetic field would make empty space itself act like a polarizing crystal, twisting light that passes through pure vacuum, and in 2016, astronomers reported exactly that signature in the light of a neutron star. Vacuum birefringence observed. Even nothing, examined closely, turns out to be made of the same field as light, and the strangeness is not reserved for relics and rarities. In May of 2026, just weeks ago as I speak, researchers reported producing entangled photon pairs joined in the uncanny quantum correlation that troubled Einstein, not from precision lasers, but from ordinary sunlight. The result is new and awaits the slow grind of replication, so hold it gently. But its suggestion is lovely, that entanglement, long treated as a hothouse flower of the laboratory, may be growing wild in plain daylight, woven into the most ordinary light there is. So the ocean is everywhere, ancient, unobserved, and quantum to its bones, and that completes a circle our thread has been drawing all night. The universe is mostly made of the very thing this entire video has failed to pin down: timeless, identityless light, almost all of it travelling forever, without ever being asked a question by anyone. Which leaves only the rarest event in the cosmos to consider, the exception to all that solitude, the moment when a question finally gets asked. It is happening right now, a few centimeters behind your closed or closing eyes. The last part of this story is about the meeting place. Is less than break time equals 1s is greater than number, part 12, the light that looks back. Let me gather the whole night into a single slow sweep, the way you might run a hand once more over a finished carving. The ray of Newton died in 1801, killed by stripes of darkness where brightness should have been. The pure wave reigned for a century and died in 1905, killed by a metal plate that counted its lumps. The reborn particle never explained the stripes, and so the truce of duality was signed, and then the truce died too, one photon at a time, dot by dot assembling patterns no single path could paint. Einstein's last hope, that light at least possesses some definite nature beneath our clumsy questions, outlived him by 70 years, and died in 2025 in a lattice of cold atoms in Massachusetts, where the wave faded in exact proportion to what the universe was permitted to know. Every picture collapsed. That was the thread, and it held to the end. What stands in the wreckage is the strangest portrait ever drawn of a familiar thing. A photon is an excitation of a field that fills the universe, with no clock, no path, no location, no point of view, no story between its appointments. It does not endure the way you endure, persisting patiently through the hours of the night. It is more like a verb than a noun, a single completed touch between 2 points in space-time, and all the in-between we imagine for it, the soaring, the travelling, the crossing of the dark, belongs to us, the slow ones, who cannot help telling stories about journeys. But the portrait has one warm corner, and you are in it. The abstraction becomes an event at the meeting places, and your eye is one of the universe's meeting places. When a rod cell in your retina catches a single photon tonight, that catch is the moment the entire formal machinery, fields and amplitudes and probabilities, condenses into a fact. One quantum of light, which had no biography, acquires its single line of history, absorbed here, now, by you. Of all the light in the ocean of Part 11, almost none ever gets such a moment. By count, observation is among the rarest things that ever happens to light. You provide it simply by looking, and when the light you catch is starlight, the meeting carries its full strangeness on its back. The light of a star 1,000 light years away crossed 10 centuries of our time to reach you, and by its own missing clock, no time at all. For the light, the surface of that star, and the back of your eye are a single touching instant. You and the star are pressed together in the photon's non-existent moment, partners in the only event it will ever have. I told you in Part 2 that you have never seen your own face, and that is still true, and I owe you the kinder half of the thought. The messenger you have trusted your whole life turns out to be the strangest thing physics has ever examined, and it has carried the universe to you flawlessly anyway. Every colour invented by your brain, on schedule, every star delivered on time, after a journey it never experienced. Einstein confessed, near the end, that 50 years of brooding had brought him no closer to knowing what light quanta are. It has now been 120 years, and the honest answer has not changed, only sharpened. We know what light does to a precision of 1 part in a trillion. What it is may be a question the universe answers only in the moment of asking, and never in advance, and never on the record. That is yours to fall asleep on, and it is a good companion, the kind of question that asks nothing of you. So here is the last thought, and then I will let the dark have you. The universe is, by count, mostly light, and nearly all of it streams on forever unmet, unmeasured, unasked. Light only becomes fully real in moments of contact, and moments of contact are nearly nowhere. But tonight, behind your eyelids, dim as it is, contact is still quietly occurring, and every glance you have ever taken at the night sky completed a journey that, for the traveller, took no time at all. In an ocean of unseen light, looking may be the rarest thing that ever happens to it. The stars cannot know it, and the photons have no way to remember it. But for a few seconds tonight, you were the place where the universe finished a sentence it began before the earth existed. Sleep well in the middle of all that light,